Okay, yeah. So real and complex eigenvalues. So let's just make up something. Let me see what I want. Let me think about it for a second. Let's say I want. Let me say I want my let's say that I want I want the equation. What do I want my characteristic polynomial to be? So I want my characteristic polynomial to be z squared plus 6z plus 10. Yeah, that's what I want. And so if I want this to be the case, working backwards, if I'm trying to come up with a 2 by 2 example, then I would want minus trace a to be 6, and I would want determinant of a to be 10. All right. Okay. So I want minus trace a to be 6. I want the trace of a to be minus 6. There's a few ways I could do this. So let's do minus 2 and minus 4 here. So that gives me trace of minus 6. So minus trace a is 6. And then I want the determinant to be 10. So minus 2 times minus 4 is 8. And I would be subtracting 2, multiplication of 2 entries here. So I would have 8 minus minus 2, and I'd be good to go. So let's do 1 and minus 2. Okay, so here's my A. Right now you have seen the sausage making process. John, the exam will be posted today sometime. So your final exam will be posted today at some point, and you turn it in on, I think, Thursday is the 17th. So that's when it'll be due. Okay, so now forget that I wanted this. Let's do an example. A is minus 2, 1, minus 4. Okay, and now I want to find all eigenvalues of A, since that's what was asked. So find all eigenvalues of A. Well, I need to find the characteristic polynomial first. So characteristic polynomial is yeah, I could write this of z or of lambda, whatever. So this is lambda squared minus trace of a, so that's minus 6, so that's plus 6 lambda. Plus determinant of a, which if we've done this correctly, this is minus 2 times minus 4, so that's 8, minus 2, so that's 10. Oh, wow, how did it work out so well, right? And now I want to put this equal to 0, right? I want to set this equal to 0. So why did I want this? Because this thing is, I can always use, the quadratic formula if I want to. But in this form, it's actually really easy. So note, this is lambda here, right? To give you the hint on how to do this quickly without using quadratic formula. So this is lambda squared plus 6 lambda plus, what is this? Like, it's plus 10. What would we be happy with? If this 10 was what? All right, so if that 10 was blank, we would be happy. So fill in the blank there. And I will play music until someone fills in the blank. Yeah, 9, exactly. Okay. So the idea is this is 9, but of course it's not really 9, it's 10, so it's 9 plus 1. Okay. But this factors, right, nicely. This is lambda plus 3 squared, and this is plus 1. Okay, so if I set this equal to 0, right, then lambda plus 3 squared is equal to minus 1. Oh no, how do I solve this? Oh, well, lambda is equal to minus 3 plus or minus I. Right? Okay. So, you know, if it's something stupider than that, then clearly, like, if it's something where you can't conveniently do something like this, it's not a problem. You can always just use quadratic formula, right? So yeah, you can always use quadratic formula if this is something terrible. Use quadratic formula, and that immediately tells you, right? Just compute the discriminant, and the second you compute the discriminant, you know if the discriminant's negative, then you've got complex roots, right? Well, if it's equal to minus 2, you do the same thing, right? So if it's equal to minus 2, you'd have say you had this instead, right? What would you do? Like, well, when you went to take the square root, right, it'd be lambda plus 3 is plus minus square root of minus 2. Well, you know, oh no, this is minus 1 times, so this is, you know, square root of minus 1 times square root of 2, right? So this is plus minus root 2i, right? So it's the same deal. So in that case, lambda would be minus 3 plus minus root 2i, right? So it doesn't matter. So, you know, you could handle it like that. Of course, you don't have to. You're not always going to be in a situation where you can complete a square nicely. So, you know, you can always just use quadratic formula. So, like, this is something just to save you time. Of course, there's no guarantee you can always do this. So just use quadratic formula. Right. In fact, if you use the discriminant, right, if you use b squared minus 4ac, right, if this is positive, what do you have? You have 2 real eigenvalues, right? 2 real eigs. If b squared minus 4ac is 0, what do you have? 1 real multiplicity 2 eigenvalue. And if b squared minus 4ac is less than 0, you have 2 complex eigs, right? So that's the deal. The point is, you have, for a 2 by 2, right, it's a degree 2 polynomial. There's just not a whole lot of stuff there's not a whole lot of options there, right? It's just a quadratic, so it's a parabola, right? Move the parabola around, right? It either crosses twice, crosses once because it's tangent to the x-axis, or it crosses 0 times. Okay, in which case you have complex roots. Okay, for the MATLAB project, is it okay for there to be a complex number when it says exhibit Eig A? Yes, that's fine. That's okay. So when it says exhibit Eig A, it wants you to show what the output is. So that's fine. Advice regarding problem 2 in the MATLAB. I don't know what that is. I'll have to look. Let's see. What's problem 2 in the MATLAB? So, my advice for problem 2 is that you put the basis script E into, put it into a form that you would understand. So if you have, so basically my advice is that script E is the standard basis for that space P3. Okay. So unravel what I mean by that, and you're good to go. Let's see here. John, on the MATLAB, if you have stars in entry, can we assume the value is 0? There's a way to, well, so John, if you have that happening in MATLAB, it probably means that something is wrong with the format. That's usually a format issue. So you can usually fix that just by changing your format. And go over a constrained optimization problem where the quadratic form has cross terms. Yeah, sure. So let me pull one out of that section. Let me see here. Let me see if I can find something decent. Well, let me see what I want to do here. You can continue asking questions while I'm trying to find a good example. It wouldn't take me too long. Okay, I think I found an example that will do, since someone else asked for a change of basis problem, this kind of does both at the same time. Actually, we listed out one of these, or at least part of this example in one of the lectures. Let's start out with the quadratic form. Let's actually start out with the quadratic form. Q of x is x1 squared minus 8 x1 x2 minus 5 x2 squared. And yeah, John, I think there's only 4 homework assignments. That's right. If this is my quadratic form, and let's say that I'm asked to, find the min max of Q of x. Of course, you can also do this with you can do this with Calc 3 as well, but you don't need to do that. So in this case, how do I find the min and max of this thing? The idea is first I'm going to do a change of variables here, so this is a change of variable to a variable where the associated quadratic form to this thing would actually have no cross terms. So what is the associated symmetric matrix to this quadratic form? Well, I know what the diagonal entries are because I know what the pure entries are. So I have 1 here and I have minus 5 for the x2 term. Then what's the x1 x2 and x2 x1 term look like? It would have to be minus 4, right? Each of those would be half of this. Okay, looking at this thing, here's my symmetric matrix that gives rise to the quadratic form. So if you were to actually check this, what you have is that this is actually X transpose A X. Again, and you could check that if you really wanted to, but we're not. We're just going to go here. So the idea is I want to find a P. So find some P that's invertible. In fact, it's going to be better than that. It's actually going to be orthogonal. For these things that we are going to do, but a general change of variable is the change of variable x is equal to p y, or you can write it in the other direction too. So y is p inverse x. What's nice is if this is going to be orthogonal, this is actually p transpose x, and we want to find this in order to actually transform our quadratic form x transpose ax to this. So by plugging in here, this is py transpose a times py, which after I do all this and associate, I get y transpose p transpose ap. Right, y, and the idea is I want to find a p that's invertible and orthogonal such that a is p inverse dp, right, or p transpose dp in the case of this being orthogonal, where d is diagonal, right? So I want to diagonalize a, and ideally I want to orthogonally diagonalize a, but hey, I'm in luck. If you have a symmetric matrix, that's exactly the kind of matrix that is orthogonally diagonalizable, right? That's what we did in the first section of chapter 7. And so this is a diagonal matrix, okay, which is more convenient to deal with. Okay, and then anything that we wanted to do here, we do it in y, and then to go back to x, well, x is just py. Right, and so how does that apply to what it is we're doing here with A? So the idea is I need to orthogonally diagonalize A first. So orthogonally diagonalize A. Of course, the fact that it's an orthogonal diagonalization is you only have to do one extra thing, right? So orthogonally diagonalize A. Orthogonally diagonalization, that doesn't make sense. So orthogonally diagonalize A. So if you orthogonally diagonalize A, here's my matrix A. I'm not going to go through the whole process, so we've done a lot of diagonalization. So find eigenvalues, eigenvectors. Turns out the eigenpairs are 3, 2 over root 5 minus 1 over root 5. And the other eigenpair is minus 7. And the eigenvector associated to it's 1 over root 5 and 2 over root 5. And so the P matrix that we seek, we can form from the eigenvectors. So this is 2 over root 5 minus 1 over root 5, and 1 over root 5, 2 over root 5. Okay, so there's my matrix P, and my diagonal matrix D that diagonalizes this thing is 3, 0, 0, minus 7. Okay. So then we do the change of variables, that is x is py. When we do that, what do we get? We get that the quadratic form we started with, which is x1 squared minus 8 x1 x2 minus 5 x2 squared. Okay, this is x transpose AX, but this is the same thing as y transpose DY, but that's 3 y1 squared minus 7 y2 squared. Okay. And this thing is actually easy to diagonalize, or I mean, sorry, this is easy to figure out the max and min for, right? If you have a quadratic form thing associated, so forget that it came from something else. You have a quadratic form thing associated to this. The eigenvalues and eigenvectors are actually easy, right? So it's 3 and minus 7 here, and so the max, right, happens at and what is the max? The max is 3. Happens at when y1 is equal to 1 and or it happens in that direction, I should say. And y2 is so I should say happens in direction. And y2 is equal to 0. Now, the reason I say in direction and not exactly what it is, because obviously you could make y1 equal to whatever, 2, 3, 5, whatever. And of course, this max is determined by the eigenvalue you get here. I didn't actually even put a constraint on this, right? So I didn't put any constraint on this. The idea, though, is that once I put a constraint on it, to go back to what this is in terms of x, I would just, whatever y values I get here, I would just say let x be p y. So that p that I had on the previous page, I just multiply that by y. Now I'm showing like everything that goes into this finding max and min. The idea actually is that we can skip a lot of that by just using the theorems that we came up with, it was called Theorem 6, but I don't think I gave it a name. I might have just called it the max-min theorem, or I might not have even given it a name when we did in lecture. But the point is that, if you look at the graph of this thing, of course, this is like one of these like paraboloid things, and so it's going to Like, in this direction, it can get as big as you want it to get. So I would have to put some constraint on it to for us to care. But the point is, the second I put that constraint on it, I just pick one that satisfies for the for this thing, and then I move it back to x by multiplying by p. Okay. Let's see here. Gustavo, when I say that we use Lay's terminology for range, just what that means is that just the same terminology we used. So the range is not the codomain. That's all that means. And for MATLAB 5C, oh yeah, well, so the other question you had, Gustavo, about 5C, the only difference with writing it that way, and you can't have one without the other because you have invertibility. But the difference in doing it that way is that what we called P is now a P inverse. And so if you wanted to set it up in the right way, right, then it would be the inverse of the thing you're finding is what we are setting up when we arrange our eigenvectors in the way that we did. So you would be setting up the inverse instead. But I mean, it works the same. It just reverses the order of the process. Let's see here. Doing a linear regression problem. You don't have to worry about a linear regression problem. It's not going to be on your final. Yekta, yeah, I didn't actually put a constraint on it. If I wanted to put a constraint on it, I could put. Let me find where's my paper. I was doing that, yeah. So if we put constraint on it, like here. Right. So if I put this constraint on it that it's a unit vector, then now I can eliminate this in direction, and my max happens here, right? Because this is unit vector. If this is positive at all, I'm going to get this -7 contributing. So max clearly happens here. The min, which is -7, happens at y1 equals 0, y2 equals 1. And so if I wanted to actually see what this was in terms of x, since this is what I started with, I would need to multiply this. So let's go back. We can say, so what is the x value where the max happens? So to compute this, this would be x is p, which is, where did I put my... Oh, here it is. So x is p, which is 2 over root 5 minus 1 over root 5. 1 over root 5, 2 over root 5 times y here, which is 1, 0. And so this would be so this would be 2 over root 5 minus 1 over root 5. So so I have max of 3 at x is that vector, 2 over root 5 minus 1 over root 5, and a min of -7 at x is, I'm just going to do it in my head here, so I'm still using p here, and I'm multiplying by my other vector, which is 0, 1. So if this were 0, 1 instead, I would get 1 over root 5, 2 over root 5. Now, there's an easier way that we could have done, right, if we had thought about something. Again, using that theorem, as I said, all I had to do here was state what. Because what did you notice about these? All right, what do you notice? What do you notice about these two things? So what are those two vectors that I have arrows going from? They're the eigenvectors, yeah. They're the eigenvectors you started with. They're actually the columns of P. Right? So they're V1 and V2. But this is exactly the theorem that we had, which stated that the max was the largest eigenvalue, which is 3, and where that occurred was at the eigenvector associated with it. And the min was the smallest eigenvalue, and where that occurred was the eigenvector, right, associated to it. So this is it's theorem 6 in my version of the textbook. I can't remember what I called it when I wrote it before, but here's what it looks like. So this is theorem 6. So A is symmetric matrix. Define little m and big M. I'm not going to go back to the previous page. Then big M, this is the max value, is the greatest eigenvalue of A, and little m is the least eigenvalue of A. And the value of big M is obtained when x is a unit vector corresponding to big M, and the value of that is obtained when it's a unit eigenvector corresponding to little m. That's why we needed this to be an orthogonal diagonalization, because we need those eigenvectors to be unit anyway. And it turns out to be orthogonal diagonalization anyway, because A is a symmetric matrix, right? When you're dealing with quadratic form, you're dealing with symmetric matrices, so everything's nice. Yeah, Gustavo, email me. I have some time this week. Sam, the constraint is unit circle in x coordinates, but of course you don't have to give the answer in y coordinates. You can transform back to x coordinates. So your question is, does P guarantee that the length is conserved? So the idea is that, so it's an orthogonal transformation which does preserve length. And the reason that it does preserve length, that's a really good point to bring up, is it actually preserves length when you have, not just for orthogonal matrices, they're a nicer thing. Remember when we first talked about orthogonal matrices, we defined rectangular matrices that had orthonormal columns. And we didn't call those orthogonal matrices because we wanted to reserve orthogonal matrices for when it was square. But it turned out that they have the property that you are mentioning, that is they preserve length, even when they're not square matrices. So let me find it. There's a quick list of, this is done at, I believe this is done in the early parts of chapter 6. Let me make sure I can show you where. Here we go. So this was called Theorem 7 in this part of it. Here, let me make this not blurry. So this theorem gave some nice properties of these matrices that had orthonormal columns. So first of all, an m by n matrix U has orthonormal columns if and only if U transpose U is the identity. But also, these are the things that we're really interested in. So let U be an m by n matrix with the orthonormal columns. Let x and y be an Rn. Then the length of Ux is the length of x. So that answers your question. And then you get these other properties that actually give you this. So when you dot Ux and Uy, it's the same as dotting x and y. So they preserve dot products as well, which is why this is preserved. And these are orthogonal if and only if x, y are orthogonal. So yes, the answer is yes, they do preserve length. So moving from one constraint to another in this case is not a problem at all. In fact, orthogonal transformations are one of the key things used to define Euclidean isometries. And you know that isometries are examples of things that preserve length. Like that's the definition of isometry. So these orthogonal matrices, which are, in the theorem here, the orthogonal matrices are they're not even, these aren't, these are more general than orthogonal matrices. These are just a rectangular matrix with orthonormal columns. An orthogonal matrix is a square matrix like that. Okay. So anyway, those orthogonal matrices are used in defining Euclidean isometry, so they definitely preserve length. So yes, that's a good thing to check, that you can go from this constraint to the other. But yeah, you can. When you're dealing with orthogonal matrices, you don't have to worry about that stuff. Okay. I show my face. Hold on. Let's see here. Let me see. Can I add a capture device in live time? Maybe. Let's see here. Add existing. No, that's the, hold on, that is exactly, that's just a copy of mine. I'm going to have to add another one. So I don't want to, I want to remove that one. Okay. Let me create new video capture device 2. Okay, it's not rotated or reflected or anything. So yeah, here's here's my setup right now. Oh, what's up with the scaling here? Oh man, it's getting like microscopic. Oh, I see. What in the hell? It's like keeping it rectangular. There's no way I can drag this. I can't drag this thing around. I guess maybe I have to change the aspect ratio in the actual settings. But anyway, so yeah, that's the deal. Well, so the original reason I didn't want to was mostly just because I didn't want to have to worry about constantly moving the display around. When I was worried I would be writing underneath it. I wanted maximum screen real estate, and I didn't know that an image of me writing on a piece of paper, because this is me now sitting looking into the camera, but mostly it would have been, I would have had to move this around, and it would have just been, this would have been the view, me writing like this. I don't know that it would have added that much to what was going on. But anyway. I'm going to put the tunes back on until I get more questions. okay. I think, am I back? Let me know if you can hear me. Let's see here. Yep, I can hear you. Okay, cool. Okay, yeah, I don't know what happened there. Like the stream was still going for some reason, but like I couldn't actually do anything like in my streaming software. It was like totally locked up. Anyway, oh, Megadeth Metallica. I mean, uh, early Metallica and then Megadeth is my answer. Change of basis problems. Yeah, let me see if I can find. Let me think of a decent one. So let's see here. What do I? Okay. Yeah, here's an example. So let b1 be the vector 1 minus 3, b2 be the vector minus 2, 4. So script b is b1, b2. And let c1 be the vector minus 7, 9. And c2 be the vector minus 5, 7. And script c is c1, c2. So these are both bases for R2. You can figure that out pretty quickly. I mean, they're linearly independent because they're not they're not scalar multiples of each other. So so both of these are bases for R2. So then first part, find the change of coordinates matrix from C to B. It's blurry. Why is that? Huh, it's not blurry on my screen is the problem. No, it's weird because on my actual capture screen it's perfect. But on YouTube it looks blurry. So I don't know what's going on. Let me restart the string. Refresh page. I will try to do the same thing. Let's see here. Oh yeah, it's fine. Okay. All right. So yeah, it was doing the same thing to me even from my like dashboard view. It was giving me that it was blurry. Yeah, I think that is what happened. Basically, when the stream was in the process of restarting, it was automatically, yeah, the quality was getting shifted down. Okay, so if I want to find the change of coordinates matrix going from one basis to the other, how can I arrange these? So I want to compute the change of basis matrix from C to B. So the thing that I'm computing is P from C to B, right? So the thing that if I multiply on the left by it, a C basis vector, I go to a B basis vector. Okay, that's the way to remember what this thing does. So how do I actually find this thing? So I find this by setting up an augmented matrix where I've put B1 and B2 columns on the left, say, and C1 and C2 columns on the right. And then I would do row operations on this thing until I have the identity matrix over here. Okay, and so if I write this out, I'm going to write it column-wise, so 1, minus 3, minus 2, 4. And then for C, this would be minus 7, 9, and minus 5, 7. Okay. If I do row operations to make this the identity, what I get is that this is 1, 0, 0, 1. And this is, so let's see, this would be 3 times, I'm just going to go ahead and write the final thing. So this is 5, 3, 6, 4. And so this matrix here is my, so P from C to B is the 2 by 2 matrix that shows up in that block. Okay. Now, what if I wanted to find the change of coordinates matrix going the other direction? Well, in that case, I just find the inverse of this matrix. Right. So if I wanted to find the other matrix, let's say that for whatever reason I wanted the change of coordinates matrix going the other direction, and I'd already found this. Then the change of coordinates matrix that goes from B to C is actually just the inverse of the change of coordinates matrix that goes from C to B. So it's just this thing inverse. So it's this thing, this matrix, 5, 3, 6, 4 inverse. But inverse of a 2 by 2 is easy. So what do? I swap the main diagonal entries, right, 4 and 5. I negate the off diagonal entries, so minus 3 and minus 6 here. And then I would have 1 over the determinant here. What's the determinant? I have 20 minus 18, so it's 1/2 here. So this is the matrix 2 minus 3/2 minus 3 5/2. So this would be my change of coordinates matrix going the other direction. Okay. And so again, the way to keep track of what it is that's going on here is it's if I start with a coordinate vector that is, say, a B coordinate vector, okay, and I want to transform this to a C coordinate vector, right, then what do I do to it? I multiply on the left by the matrix that it changes coordinates from B to C, and what I get is the C coordinate vector. And the way to remember this is that this B needs to be on the same side that you're multiplying on, right? So I have B basis vector, the B is on the right because I'm multiplying on the left here, and it takes me to C basis vector. Okay, or the C coordinate, I should say. So I go from B coordinates to C coordinates. Okay. And remember that this is the same regardless of what the basis thing that you have in question. Like whatever you have going on, it's the same. And so you can very easily. This is what you do, if you have both vectors given to you in terms of the standard basis, right, of R2 in this case. But it's even easier if you already have things like, so remember finding this P is even easier if you already know, like B1 in C coordinates, and B2 in C coordinates, and so on. Right. So the thing that we did, the computation, was finding these. If you actually have these already written out, then you're good to go. You already know what the columns of P are. This is the B coordinates of X. Well, it depends on the X, Yekta. It's if you have a vector X and you can write it as C1 B1 plus C2 B2, then the B coordinates of X would be C1 C2. Sorry. So, for instance, right, if your vector X was minus 2 B1 plus 7 B2, then the B coordinates of X would be minus 2, 7. Thanks, everyone. Yeah, I mean that's pretty much it, I guess. I guess that's the whole course. We'd already done with the content for a couple days, but This is it. So I will post your final exam later today, and I'll put out a big announcement. So be looking for it. And then that's it. It'll be due on the 17th, and then your grades will be in, within a few days of that. And then that will be the semester. So, well, at least as far as this class is concerned. So you will be done with your obligations of this course by Thursday. So, that's it. So I will, hopefully have you all in some class later. But yeah, that's Math 461. That's linear algebra. So anyway, hopefully I'll see you all around.